All right, another unprepared stream. But I wanted to start work on an arena allocator at the moment, just for the fun of it. Learn a few things about memory allocation in C and things like that. So I thought, why not just turn on the camera as well and, you know, have some people participate if they wanted to. Or learn with me, essentially. Before I continue this, I just want to show something which is really cool. So the Game Boy header extractor that I worked on at the end of last year on this stream, with Visual Studio and the C runtime and everything compiled, I get an executable of, hang on, I have to... There we are, release, GB header extractor. So this is built in release mode with, all the optimizations turned on and all things like that. And it's 187 kilobytes, right? And yesterday I finally finished, finished. I moved over the GB header extractor to this new project format and I'm compiling it without the C runtime, right? And what I'm getting now is, let's remove this. There we go, 31 kilobytes. It is exactly the same functionality. Nothing changed. Like, logically speaking. I just trimmed out the fat. I'm sure it probably can be trimmed down a bit more, but like, I love this. This is... love getting rid of things that I don't need. Minimalism, yay! Okay, so anyway, today, one of the main motivations for an arena allocator, and I'll explain what that is in a second, is because I have all these different heap allocations throughout this program and stuff like that, and essentially let the operating system manage on how it allocates memory. And it's a bit annoying because you don't necessarily know where this memory is coming from, right? Is it in the same page as before? If you allocate, does it cross page boundaries and things like that? Is it going to be continuous? So if you want to have multiple allocations, they're not really guaranteed to be continuous, right? So not in an address range and sequence, basically. It could be anywhere. So to kind of mitigate that, I was thinking of arena allocators. They're quite a popular thing to use, it seems. Well, I shouldn't say popular, because the popular thing to do is just use, C++ and whatever. But I kind of have used arena allocators before already in some other projects, like in the Game Boy assembler, although I strictly speaking didn't call them arena allocators, right? What I did, I was just allocating a huge chunk of buffer somewhere, and then whenever I needed something like a little buffer of a specific size, I was just adding it into there. In a similar behavior like a stack would work. And that's essentially what an arena allocator is. It essentially is just reserving a whole chunk of memory at once, committing a page, and then you just write in stuff into the buffer whenever you need it, and you grow the buffer. And if you remove stuff, you just wind it back by a few bytes, right? So you don't have to do all this heap alloc and get process heap and stuff like that. And the address will be continuous because you essentially reserve a whole chunk before the program starts. So you have an address range reserved for your whole program lifetime, which is quite nice. So yeah, so I essentially wanted to write a header file for this. So similar where I have this, so on Danilib, we have this Dani path file right here, right? And I should probably copy. So I should copy this one into here, because that's the final version. So I essentially want to now create something that's called Dani Arena, for example. So whenever I want to use Arena allocators, because in some projects I maybe do not want to use them, I can just pop in the headers whenever I want to, and then use that method of allocating memory essentially. So let's go with that. Let's just create a new file. Nope. I was looking at the red debugger source code previously as well, and there were some nifty things in there, some of which I'm going to copy. Some. They also use arena allocators, by the way, which is quite interesting. I will sort of have a little bit of a different approach than theirs, but yeah, we'll see. So source, and what we call this is Dani Arena. Right. Cool. And I'm sort of copying the same pattern here. So we have Dani lib arena. Right. And this will be Dani arena decorate. And this will be Dani arena. And if, and then we have if defined Dani arena implementation. And let's make a little note so I know which endif belongs to what. Yeah, basically. So not exactly stack allocator, right? But it is essentially just allocating a whole bunch of memory on the heap up front, reserving some, virtual memory, and then just using that buffer that you get back to as your allocator for memory allocations, essentially. So you don't have to call out into heap alloc and that sort of stuff. This is the first time I'm dealing with Win32 VirtualAlloc and these kind of things. I've never used them before, so that will be interesting. So let's see. Reserves, commits, or changes the state of a region of pages in the virtual address space. Yeah. The starting address of the region to allocate. How did I learn about those? There is an interesting blog post by Ryan Fleur, I think. Yeah, this one right here. Where he basically talks about arena allocators and what they're used for and how they can be useful and things like that. Incidentally, he also worked on the RAD debugger, which is a tool I'm using. So I don't exactly know how I got onto this page. Maybe posted it on Twitter or something and I just saw it. I can actually post the link in the chat. Hang on. There we go. Have I watched Handmade Hero? No. So I know about it. I know some clips of it. And I think I watched 4 or 5 days or something when Casey started out the series. but I've never followed it since then. And it's been going on for a few years, isn't it? I don't exactly know how long, but okay, so what do I actually need? Let's think about this a little bit. So I'm trying to use this in the GB header extractor program that I have, right? And essentially I want to reserve a bunch of memory up front, right? Well, address space up front. Commit probably 1 page worth of memory. And then as I allocate, okay, so let's start simple. Oh my god. Let's just call this arena. Arena underscore T. I kind of use the underscore T for my structs, but I'm not sure if that is really that. No, let's leave it anonymous. I don't like that anyways. So what does that have? Probably some kind of base pointer, right? Probably have the capacity and the current used size of the arena. Yeah. And then probably, so whenever I actually allocate something, probably some kind of buffer, right? And so this would be a little chunk of a whole arena. I'm probably gonna need some more fields in there or whatever, but I will figure that out as I go along and as I do the implementations, right? So what I probably would start out with is something like, I don't know, init arena, right? And that goes into the implementation right here. Oh, and what it probably returns is an arena. Do I want to return the struct like this, or do I just... probably more like... Probably could have a boolean to see whether that worked or not, but I'm not too sure yet. Okay, woo. So VirtualAlloc is probably what I want, right? So the starting address of the region to allocate. If memory is being reserved, the specified address is rounded down to the nearest multiple of the allocation granularity. If the memory is already reserved and is being committed, the address is rounded down to the next page boundary. To determine the size of a page and the allocation granularity on the host computer, use getSystemInfo function. If this parameter is null, the system determines where to allocate the region. I think this is what I will be using first. I won't be, adding all the bells and whistles of like trying to figure out page boundaries and all this kind of stuff at first. I just want like a basic system to work, and then I can slowly add all these advanced features as I learn about this kind of stuff. I have not learned a lot about it, so okay, I don't think I need to worry about a security enclave here. So the size of the region in bytes. If the LP address parameter is null, this value is rounded up to the next page boundary. Okay, so this will already be doing that. The allocated pages include all pages containing 1 or more bytes in the range from LP address to LP. Okay, this means that a 2-byte range straddling a page boundary causes both pages to be included. Okay, fine. So then we have memcommit, memreserve, memreset, memreset undo. Large pages. Okay, I won't be doing large pages at all as well at the moment. Okay. Before I try this here, maybe I should play around with it in the GB header extractor, right? So, am I in here? Yeah, cool. So where is the main function? So VirtualAlloc, right? It has an address. Let's put this to null for now, and then we have a size that we would like, right? So size t is U64. Let's say we want, I don't know, 16 megabytes, right? Oh, yeah. megabytes is 2 to the power of 20, I think. Yeah. So that's a nifty thing that I saw in the rad debug source code, which I quite liked. So these macros right here, where you can specify what kind of unit this number is, and then it converts it down to bytes. So for kilobytes, you would have something like this, right? And that's to the power of 10. And then you can do the same for gigabytes, terabytes, like so. So if I would change this to gigabytes, it would give me the byte value for like 16 gigabytes, right? But let's just do megs. And I think page boundary is 4 kilobytes. Actually, yeah, let me try and figure that out first by using get system info, because that could be quite interesting. That is in kernel 32lib as well. Cool. So I can do get system info, and I'm getting a system info struct. Oh, there's lots of stuff in there. Cool. Let's just call this info, right? And then OEM ID, processor architecture, okay. Page size, there we go. Minimum application address, maximum application address. Interesting. Active processor mask, okay. Number of processors, processor type, allocation granularity, cool. Oh, that's quite nifty. This page size is used by VirtualAlloc function. Nice. Appointed to the lowest memory address accessible to applications and dynamic link libraries. Okay. Appointed to the highest memory address. Cool. Zero's processor. The set of processors configured into the system. Interesting. Honestly, let's see what we're getting in the debugger. Yeah, that's fine. Call debug. And jump in here. And this is info. So, OEM ID, what is that? OEM ID. An obsolete member. Okay, well, we don't care then. W processor architecture. The processor architecture of the installed operating system. So for us, that is 9, which is AMD 64. Basically 64-bit AMD or Intel processor right here. Nice. Cool. Then this is reserved. Okay, page size. Nice. So 4 kilobyte page sizes on my system. That means whenever I try and get memory, it will reserve, it will commit a whole page of memory, which is 4 kilobytes. So even if I ask for like 20 bytes, it will commit 4 kilobytes. Pointer to the lowest memory address. Okay, so I see. So from there to there. This is quite an odd address. Actually, I have this Windows internals book right here, and I'm just curious because they talked about address ranges as well. And let's see if this actually is correct. Granted, it was just in the first few pages, but there we go. No, it doesn't talk about the addresses specifically. Never mind then. Okay, active processor mask, right? Can I say, give this to me in bitmap? No. It seems the rules don't work here. What if I do info, what is it called? DV active processor mask. Really? Ah. There we go. And then maybe, can I say bit? No. Bitmap? Nope. I can display it as hex, which is almost as good, I guess. Anyways, okay, so what is the processor mask? Sorry, a mask representing the set of processors configured. What does that even mean? So that will be what? So these. So what, 16 processors configured? Is that what that means? I mean, yeah, okay, logical processors is 16 on this machine, so I guess that's what it means. Okay, and then okay, could have just looked at the number of processors down here, which says 16 as well. Okay, processor type 8664. What is that? I love this huge text. 8664. This is AMD x86-64. Okay. Then we have the allocation granularity. Or is that 16 bytes? I think so. No, well, I already had it there. What am I doing? Yeah. Okay. So 16 bytes is the allocation granularity. So does that mean... Sorry, 16-bit. Jesus, 2 bytes. So... Okay. Processor level, what is that? The architecture-dependent processor. It should only be used for display purposes. To determine the feature set of a processor, use blah, blah, blah. Okay. Well, that just basically means something about my AMD processor right here, right? So like model number or something, and then there's revision. Okay, interesting. Okay, cool. So if I then, let's say, call VirtualAlloc, and my size is 16 megs, right? And I want to, okay, so we have memcommit, allocates memory charges from the overall size of memory and paging files on disk for the specified reserved memory pages. To reserve and commit pages in one step, use memcommit memreserve. Okay, so what if I just want to reserve? Reserves a range on the processor's virtual address space without allocating any actual physical storage in memory or in the paging file on disk. You can commit reserved pages in subsequent calls to VirtualAlloc function. Okay. Other memory allocation functions such as malloc and local alloc cannot use reserved range of memory until it is released. Okay, that makes sense. Ah, okay, you can reset it. Reset undo, okay. There's a write watch. And then there's virtual free. Can decommit a committed page, releasing the page stored. It can also release a reserved page. Okay. So I will be taking a look at this next. Okay, there's some example code right here. Ah, that's how they do it. And they have a page limit and then ask for basically the amount of page sizes. It's actually, that's all right, I suppose. Okay, what are these? These memory protection constants. Ooh, all right, okay. Page execute enables execute access to the committed region of pages. An attempt to write to the committed region results in access violation. Okay. Enables execute or read-only access. Okay, interesting. Okay, a lot of the things are a bit alien to me. But that was to be expected. I'm learning after all. Okay. Well, so allocation type, let's say I just want to reserve memory at the moment, right? So let's do mem reserve. I mean, instead of doing that, I guess I could say info dv, what was it? Page size, I think. I don't have this, do I? Nope. Come on. That's what I wanted. Get system info, and then we'll look here. And D word page size. Yes, that's the one. Okay, so it's 4 kilobyte pages. Let's say I want to have 8 pages. Right. And then do I need protection level? I don't know if I want execute, but page read write sounds all right. Okay. So what does this return? Whoops. If the function succeeds, the return value is the base address of the allocated region of pages. Right. If the function fails, the return value is null, and I can print a Windows error. Okay. So essentially what that means, this will be the base, right? And then if base is null, something went wrong, so print a Windows error, and we can exit the process here. Again, I don't think I need to return afterwards, but okay. So we're getting the system info, looking the page sizes, reserving 8 of them, trying to reserve them at least, and getting the base address out of that one, right? And then somewhere at the end, so we do stuff here to do something, right? It would be great if I know how to spell to do. And then I basically free the whole chunk, I suppose, with virtual free. Okay, so what does virtual free have? A pointer to the base address of the region of pages to be freed. Okay, so in this case that will be base, right? The size of the region of memory to be freed in bytes. If the DW free type parameter is mem_release, this parameter must be 0. The function frees the entire region that is reserved in the initial allocation of VirtualAlloc. If the parameter is mem_decommit, the function decommits all memory pages that contain 1 or more bytes in the range of address to blah 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 high size. Okay. This means, for example, that a 2-byte region of memory that straddles a page boundary causes both pages to be decommitted. Right. And then we have the free type. So the free type is decommit. Decommits the specified region of committed pages. After the operation, the pages are in the reserved state. Releases the specified region of pages. Okay. Ah, that's what I wanted to know. If any pages in the region are committed currently, the function decommits and then releases them. So this is like, I thought, do I have to decommit committed pages first and then call mem_release to like free the reserved ones? But I can just do that in one go by just using mem_release right here. And the size will just be 0. The size doesn't matter. Okay. And if it fails, again, can call print Windows error and that. Okay, so this is Yep, cool. So if I jump into this now, GB header extractor, right? I'm just adding a few headers here, a few columns. Okay. Wait, did that not work? What? There we go. So commit size at the moment is, what is this, 1 meg or something? Which is probably for the stack, right? And then as I continue, wait, this is committed size, right? Okay, I don't exactly know where to look for the page sizes, to be honest. But the working set jumped up. Did it jump up by 32K? Okay, no idea. Super annoying. But my knowledge on how this works is quite limited at the moment. So Okay, whatever. I'm not gonna try and figure this out. I'll figure this out off stream eventually. I'm sure this Windows internal book that I have has actually some information on this. I thought for a second the stream stopped. Oh dear. Okay, anyway, so this is... so we reserved a bunch of memory. Down here we're freeing this, right? So what would happen if I'm trying to read what's in it? Right? What if I try this? Still streaming? Good. All right. Well, something is going on there, so I think we're crashing. Let's see. So we're going to there. And then we're just trying to read from, you know, an address that's basically just reserved address. Yep. Interrupted. I thought it would say why it interrupted. No. Doesn't look like it. No, it just says interrupted. Okay. I would have to try and figure out how, if I can get some more information out of that. But basically, because this is not committed memory, right, it's just reserved, and I'm trying to access it, application goes boom. So, which makes sense, right? So how would I now commit one page? So VirtualAlloc. Do I now say base? Because now I want the address of what I reserved, right? That is virtual free. Done that. Okay, in the example, they do exactly that. So they pass in the base pointer, so that was the right assumption at least. Yay. And then you pass in the size you want to allocate. So in this instance, let's just use 1 page worth, right? And mem commit. And the page is read and write. So now we have committed. If committed is null, then we couldn't reserve it. Do an exit process right here. And now if I'm trying to access it, that should work. So, reserve 4 times 8 kilobytes, or rather 8 times 4 kilobytes, right? Actually, yeah, let me write it that way. And here we say commit 4 kilobytes. And then down here, free everything. Okay, so build, run. Okay, so I'm getting output, so it definitely goes after this line, which means I can now actually access the committed memory. Cool. So, and then as a little test, what I could do is say, well, I'm having committed and I'm trying to access, let's change this to a char pointer right here. Right, so I don't have to do that all the time. So what if I'm trying to access this, right? What am I doing here? What's going on? Why am I stuck in like a weird? Okay. And that blows up because now I'm trying to read past the 4 kilobytes that I have committed. How can I go to an address here? I've never used this in this tool, so like this is the address I want to see. Nope. Really? Is there not like a window where I can just type in? No. Oh man. Go to address, Alt G. Okay. There we go. And actually, if I would try to write something into this, let's say committed equals X, right? Let's just do that. Build. Whoops. There we go. Build and run this now. And then if I go to this address right here, we can see an X. Okay, so this is indeed like the start of that. And then well, let's see, if I have committed plus info dv page size minus 1. Okay, so that is that address. Right, and then from here on, that is basically still reserved, and I cannot write into it or read from it. That makes sense. Okay. So in terms of arenas, right, what that essentially means is this is allocating an arena and committing like a small portion of it already. And as I'm getting buffers out of it and pushing things into the arenas, basically, I have to keep track of the current size. And if I'm approaching the end of it, I just commit a new page, basically. Of only reserving space based on the page sizes, right? But what if let's say I want half of it, right? And then committing that half. I mean, I still get a page worth, right? The value is rounded up to the next page boundary. Yeah. Okay. So let's try and write this in terms of arenas, right? So what does an arena need? Well, I need the base address of the virtual address space, so where it begins. I need the size, let's say the capacity of all the reserved pages. Is there no way of getting like information back of how much has been allocated essentially? Oh, there's VirtualAlloc 2. What is this? Okay, based on the process. Base address, size, allocation type, protection type, extended parameters, and parameter count. What are extended parameters? Right. Yeah, that looks like something I don't need at this moment. Okay. Then there is VirtualAlloc X. So VirtualAlloc X is just allowing you to allocate, or shouldn't say allocate, reserve and commit for different processes, it seems. Okay, you can specifically force pages to be okay. Don't think I need that at the moment at all. What is virtual query? Point to the base address of the region of pages to be queried. Okay. So I guess this is how you would query and figure out how many pages have actually been allocated or something. If you reserved, I mean, if you provide a size that is like not based on the page sizes, I assume. So if this would be just half the amount of the page size, it allocates a page size, right? But you kind of want to know. I'm still saying allocate. Reserves a full page size full of things, but in order to figure that out, you can query the base address and get information back of it. I don't think I will be needing that, but it kind of still want to know how that works. Okay, well, I'm not going to worry too much about the query now. But what I want to know is if I now want to commit the next page, right? Because I cannot access this. So this is blowing up. Right? So what I would have to do before writing into this, let's call it committed to, right? I think I read that an attempt to commit a page that is already committed does not cause the function to fail. This means you can commit pages without first determining the current commitment state of each page. Okay. So that basically means I do not need to pass in the committed pointer, but I can just go base times 2. Right? I have some errors. 4, 3, 4. What? Oh, right. Doi. Okay, that seems to have worked. Okay. Okay, so I do not need to keep track of, you know, of all the addresses of all the committed pages, essentially. Maybe I should call it reserved. Right. And then that basically means we have an arena. And then arena reserved is this. And this would be the base. Right, and on virtual free, I just have to specify arena base to release all the memory. Okay, cool. What I probably want to store here is also page size, right? Kind of would be useful to have that information, right? So then when I call these, I can just say arena page size. So now I'm trying to think how to, you know, deal with like chunks of buffer and committed page sizes and things like that. If I don't worry about like a growable buffer, that will be quite easy. I just have the capacity and whatever the size is, right? But so what does that mean? So we have a base address, right? And then we have a bunch of bytes. I need pen and paper for this. Sorry, I do not have my tablet attached to it, so I cannot scribble around while also showing it on stream. But that would have been useful right now. But as I said, I was a bit unprepared today. I just really wanted to play around with arenas and see how far I can get and learn about VirtualAlloc and this stuff because I've never used those APIs before. So we have an initial array, right? Let's say base. I don't know how fine-grained I want to go with pages. So, I mean, what we have is the reserved capacity, right? Oh, great, I already have it down here. The overall reserved capacity. We have the actual committed capacity, right? And if those reach the same, then, you know, the arena is essentially full and we can no longer allocate things. But in the meantime, I have to keep track of how much is actually used, right? So we have reserved, committed, and then the amount that is actually being used. If used is approaching the end of committed, but we still have stuff reserved, I can then allocate another page. I'm not sure if I want to keep track of page size, but let's see how that would work. So we have the reserved size, which is this. Then we have arena used is 0, and arena committed is 0 as well in this particular moment, right? We're reserving the entire space and assigning the base. Then we want to commit 4 kibs. Right, actually do not need the base whatsoever. So if this is null, do this. So what we need is the arena base, and then I want to commit a page size worth of stuff, which eventually works, right? And then I can say arena committed is arena page size. Right. And the used indicator is basically when I'm starting to use stuff. So for example, here a byte, right? I'm using that 1 byte. What I then would do is arena used +1, right? Because we have used 1 byte. There's actual information in there. The rest from used to, so from committed minus used would be the free space that's still available, right? And then let's say arena used is the page size, which means we have exhausted everything. So arena used minus arena committed minus arena used is well, in this instance it's 0. But basically I would need to check whether it is smaller than what I'm requesting, right? Because at some point I want to request like a certain size. So, but anyway, if there's no more space, I need to commit another page. Which goes from arena base and so like this, and then arena committed is becoming this, right? I'm just committing always a page worth of memory. That makes sense. I think. Okay, let me copy this header down here. Nope. Projects, GB header extractor, source, Dani lib, Dani arena H, right? Because this is where we're playing around with stuff. And then I can just move all this stuff that I just did out into, you know, the library right here, right? So this struct essentially becomes, so page size, reserved, committed, used. That is all good. And we're using the decorator here. API design sessions, yay! I mean, that's what I'm currently kind of doing as well. So if you want to be in an API design session with me, feel free to stay. So let's remove the buffer for now. So we have init arena with the arena decorator right here. Yeah, that's cool. So this will fill out the arena, and then what we can do is also say void free arena. Right, that will be the arena. I probably want a bool, right? Let's make it a signed integer, why not? Okay. So, and then I'm just going to take this chunk right here and put it in here. So first we call get system info to retrieve the system info, and then we have the arena that's being passed in, which we're going to set to page size. Some amount of reserved pages. At the moment, let's just so it's 4 kilobytes, right? Of page sizes. How much do I want? It would probably be good if I can specify this somehow first, right? But for now, let's just keep it hard-coded. I mean, 8 pages sounds fine. For now, at least. Probably can do something like Dani arena default. So you can overwrite that on the outside for now. So that is page size, then reserved. I'm reserving that amount, which is all right. Assign it to arena base. If something goes wrong, obviously don't want to print the Windows error, but I'm just going to return with 0 because something went wrong. So arena. Wait, what do I have? I have committed and used, right? So let's say committed arena page size. I'll just write them before, why not? And then arena used is 0, right? And then this should be actually all of these should be an error. Okay. So, and then in here, right, there's a bunch of shit going on, isn't there? Okay, I just put this in the common, just because I already have some stuff in there. Why not? This is Dani Arena. And then I also want the freeing. I want that in here. And what we're going to have is arena base. Right, and then could make it a null pointer. Why not? I can't type today. Used, reserved, committed, page size. I don't care if it's still filled out or not, whatever. Okay. So now I can at least create memory arenas, right? So I would use this as follows. I have arena. This is my arena, right? Creative naming. If not, Dani arena. Init arena. And then we have like so. Otherwise we print the Windows error, exit process 1 and return. Right, so this is all of that code. And then while using it, after a while, I'm going to free everything, right? Okay, let's get rid of that. So let's say this is the whole application arena. Let's call this just arena is fine. Okay, so this arena lists for the whole duration of the application, so I can basically just free it at the end if I would want to. But I mean, if the process dies, everything's freed anyways, right? The exit process function automatically releases virtual memory allocation, so it's not necessary to explicitly free the pages when the program terminates. Fantastic. I mean, since I have exit process throughout, which I can also make a little bit nicer, right? So this is program start. I could do like a proper main function, really, if I wanted to. First of all, let's get rid of this. And I can copy these into the arena stuff as well, to be honest. No, you know what? Let's just leave them common for now. It has nothing to do with that library, right? It's just something that I want that's convenient. So at the moment I'm calling exit process everywhere, which is not quite nice. What I could do is something like int main, right? And then have an arena that is being passed in, right? And then basically take all of this code, actually even better, can have arena and options being passed in. Well, not quite. That doesn't make quite sense, does it? Anyways, let's not pass anything in for now. What I wanted to say is basically I can make this just a little bit nicer so I don't have to call exit process anywhere, and I can guarantee that it's being called even if I just return from main. In any case, it will be called, right? So I could do something like that. And then just have something like return 1, right? So change all of these to return 1. Right, so something like that. Just to make sure that I don't forget to call exit process somewhere and just return out of it, and then the process would essentially just hang, which is not ideal. So that's just a little bit nicer. I could then hoist out little things as well, like for example the arena allocation, which I know happens all the time, or like the reading of the command line options that can all happen in here in program start. And then I can have this main function just focus entirely just on the code, you know, on the program logic, essentially. It's really what the C runtime is doing as well, like basically just emulating the C runtime at the moment. And actually, let's take the arena out because so arena T, arena, right? So this lives for the entire program duration. Yeah, that's fine. And then just pass in the arena. Address of arena. And then at the end, so whenever I go out from here, what I definitely need to do is Dani arena free arena. Right. Do I care about the result? Probably not. But really, I don't need to do this. Like, not really needed. OS is taking care of that. Right? I'm not sure I'll leave it like this. This is more or less just an example, but okay, so I get the arena. And then what I want to be able to do is, let's say I want to allocate a little space on that particular arena. I need to have some functionality now where I essentially can get a buffer out of it, right? So similar like malloc would do. So imagine something like we have a buffer, right? A buffer type. And I say malloc, right? Or, sorry, arena alloc, right? Pass in the arena and pass in the size that I request. I don't know, 33 bytes or whatever. So now I have a buffer that, you know, points to the start of these 33 bytes and then actually also has a size or a length rather that is 33. And then it is up to me on how to use them throughout the program. If I wanted to free that, I would call like arena free, right? Although that's not quite true because it works more like a stack. So calling this alloc is a bit misleading. So actually what this is like is a push or pop. Well, it depends from which way you're looking at it, right? Let's call it arena get, and then you can say rewind by 33 bytes, right? So effectively making this buffer go away. But the beauty of this is you don't really need to keep track of that buffer, and then, you know, if you have, let's say, like, I don't know, 20 different buffers, you do not need to free every single buffer separately, because what you do in the end, you just free the entire arena, which will, you know, get rid of that. So what you then have to imagine, you would have basically multiple arenas throughout your program, depending on what you're doing. So for example, you have, let's say you have an assembler, right? And you assemble 3-4 different files. You could have a file arena that only lives as long as the file parsing is active, right? And then you have an arena that lives throughout the entire lifetime of the program, because you want to keep track of that data and keep it in memory the whole time. Things like that, essentially. I'm probably explaining this very poorly. So now I'm wondering what the APIs should look like. Naming and stuff is a bit hard. I mean, if you... I was just looking at Ryan Flur's article here, and that is actually a good way of imagining that. So seeing the arena as kind of a stack. So if you say arena push, you're essentially pushing bytes onto the stack, which is essentially your allocation. And once you're done with it, you can say arena pop, where you know, pop a certain amount of bytes. You pop them off the stack so they're usable for something else. So something like, yeah, actually that's fine. I can always change the names if I don't like them, right? So let's say we have push. And then pop. So we're pushing a buffer onto the stack, or we're popping a buffer off the stack. Although I'm not sure how often you really need this, unless it's something that like is only very short-lived, like a temporary string or whatever. You use it temporarily for some manipulation and checking, and then you pop it back, I suppose. Otherwise, I imagine what would happen is like you just push, 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 and then say arena free, and that's it. So, and that has a base address and a length, right? Probably what I want is so in push, what would then happen is we need to check if there is enough space, right? So in that will be committed minus arena used, right? And if this is bigger than length, bigger or equal than length, I suppose. Well, I was thinking about overflows here as well, so I kind of... No, that is okay. So here we're committing more pages, if that is the case. If not, there's enough space in the arena, so I can just do buffer base is arena base plus arena used, and then say and then arena used I mean, I wonder if this buffer thing here is actually really necessary, because like I know what the length will be based on what I pass in here, right? And I could just return the pointer to the base. So this whole buffer struct is just, if I really need that throughout my program, I can then assign the base and the length to the buffer myself, right? So making this mandatory is kind of a bit shit. So let's remove that and say, really what we're doing is this. And this. No, we just do that. We're just requesting bytes, really, right? So let's call it size instead. Maybe I should call this request and free or something. I don't know. So this will be size. And this will be a void pointer. And instead of buffer, like I said, so arena committed minus used is smaller than length, then I need to commit more pages. Otherwise, what I'm going to do is say char result equals arena base plus arena used so far, right? Let's make it like so. And then I say arena used plus equals the size. I need to change this to size as well. And then what I'm going to return is just the result. Because now I got some memory. Right? Cool. And if I wanted to give this back, all that I'm saying is arena well, if arena used is smaller or equal than size, right? I can just say arena used equals 0. I don't think I need to return anything, to be honest. Oh yeah, I already had this as void up here. Because, like, why do I care whether this succeeded or not, right? I'm just giving it back to the arena. The committed size still stays the same. I could have later some functions that I, like, you know, reducing the committed sizes or whatever if I really needed to, but I don't think that makes any sense right now. I'm just trying to push and pop some bytes off the stack, essentially. That's all I'm trying to do. And otherwise, what I'm just going to do is say arena used minus equals size. So now, committing more pages, that would happen with this thing, right? But I need to so if it is bigger than the page size, then I need to do, you know, something specific because I need to allocate more than one page. However, anything else, I can just commit one page, right? And then say, okay, arena base. And what we want to commit is the it's basically arena committed plus arena page size. If that fails, return null. Size. My dog is begging for attention at the moment, so sorry about that. So let's have commit size. And the commit size is arena committed so far, right? If size is bigger than page size, then I need a few more pages, and I'm trying to figure out how many pages, right? So what I then can do is say commit size plus equals pages times arena page size, right? So that is the new commit size that I need. Otherwise, commit size plus equals arena just one page size. Okay. But then if the overall new commit size, maybe I should name this new commit size. Hang on. New commit size. If the overall new commit size is bigger than whatever we have reserved, that is a no-no, right? We cannot accommodate that, so we just give up. Otherwise, we're going to down here and just say new commit size, right? And if that fails, we return null. Otherwise, arena committed equals new commit size. And then what we're going to do is go to base, say plus arena used, increase the size, but now this actually points into a valid buffer, which I then can use. Now, this has a few problems. For example, it is not taking into account page boundary sizes and that kind of stuff, right? So let's say this is page 1 of memory, right? Which is 4 kib. And then page 2, which is 4 kib, right? What we can end up with right now is have something that crosses both pages, because you're writing at the end of page 1 and you're crossing over to page 2. Now, in the virtual address space, it doesn't really matter because the address is contiguous anyways. So you can still access it as normally. But since those are virtual pages, this could be in completely different RAM blocks that are not contiguous. So this could be in, just to simplify this, right? So this could be actually in real memory from location 1 to 20, right? And this can point from location 50 to 60, or 50 to 70, right? Or let's say 0. So then our object that we're writing then would basically start at address 20. Then there would be a huge gap of real memory, and then it would continue over here, right? Now the virtual address space kind of resolves that for us, but in hardware terms, that means, you know, we have to go to a completely different location on actual hardware to fetch the rest of the data. And that means you're kind of invalidating the cache, so everything that the processor already has cached then just gets thrown out, and yeah. So you basically don't want to cross page boundaries with objects. So if an object is big enough, you would just leave the last part of this page simply empty, right? And start the object on a completely new page. But then, if you have larger objects than pages, well, then you're kind of out of luck anyways, unless you try and allocate larger pages, which Windows has the ability to, but I do not account for that either right now. So there's lots of room for improvement in this APIs, right? This is just like all very basic, but let me just show you a use case right now. So because now we actually have something that is kind of usable. And this is where I'm also going to end the stream because I'm going to have to walk my dog right now. So basically what I can say is, hey, I need some memory, right? Let's say I want to have an array of 20 bytes or whatever, right? So I can say Dani arena push. We taking this arena and we want to push 20 bytes onto the stack, right? The beginning of these 20 bytes would be here. So let's say this is my array, right? And now I could start populating it. So from 1 to like so, right? Actually, let's make this 19. So like so. Then I can say array I equals, I don't know, let's just write a bunch of x's, right? And then on the last item, I'm gonna have a zero termination character because I want this to be a string, right? Then I can print this onto the console, like for example, print output len, I think I have. I can pass in this array if I wanted to, and I can say, hey, this is like 20 long, right? So please write that. And then now that I'm done with the array and I no longer need it, I can then say Dani arena pop, and I want to pop 20 bytes off the stack, right? So now they can be reused for something else. Again, probably wouldn't call this a lot unless it's for something really temporary like so, and where you just need something real quick and then you're like giving it back. But for all the other strings that I like build up throughout this application, I would essentially just always call push and request the exact amount that I need for the strings and then just write into them and just keep them until the application ends, right? So yeah, I wanted to build this. Okay, cool. So we have some errors. Let me fix those. Oh my lord. Okay. let's start in Dani Arena. What did we screw up? 33. What's wrong there? That is correct. That would be info. Okay. Function already has a body. Right, because I accidentally put the same name in there, which is not great. Okay, so this is the header fixed. Now let's fix the issues here. 472. Wait, 472? No, 427. 427. What's wrong here? Oh, right, the type is called Dani Arena. Oh, yeah, okay. I really have to work on those prefixes. They're quite a mouthful, and like this is just atrocious, right? Dani Arena. Almost sounds like a song. Yeah, that's not great. Okay, that was it. That was just the name. Fantastic. Okay, so if I run this, it should just... There we go, and we print out the X's. And I don't have a new line character here, so that's why I print out all of these, but I can actually change that real quick. Let's just say 18, right? And array 18 would be a new line character, for example, right? There we go. Now, after I call pop, the array would still be populated, right? And it's still usable. But, I mean, if you're using this after you called pop, that's kind of your own fault anyways. Like, what are you even doing? It's essentially supposed to be seen like a stack. Okay, well, that's not too bad of a first attempt for like this kind of library. I learned about VirtualAlloc, kind of learned how to use it, which is interesting. And now I can go and refine it as I need it. And I definitely want to work on the page boundary stuff and things like that. Have to change the naming a little bit, just so it's a bit nicer. But anyways, I'll leave it at that for now. Yes. Cool. Well, but I'm definitely going to remove... No, actually, let's just allocate the arena. Whatever. Doesn't really matter. I should probably remove this code, though. You know. And then use the arenas whenever I read like command line and stuff like that, or get the executable name, right? Because you remember when I got the executable name, hang on, where is it? Up here, I used heap alloc, which I no longer need to use. I can basically just request however much I... Yeah, I basically request the bytes from the arena instead. That's it. Yeah, don't know what else to say to that, so I'm gonna just stop here and gonna take my dog out in the windy weather. And I see you guys next time, I suppose. I streamed for 2 hours, even though I didn't want to. I thought this was just gonna be an hour, but I kind of got lost in details again. All right, see ya, bye.